Welcome to our next lesson on linear algebra, as we've started with basis and dimensions. Okay, so we have this problem here that we want to show that the given set of vectors in the 2 by 2 square matrix vector space is indeed a basis for the 2 by 2 square matrix vector space. And to show this, there are two things we mentioned earlier that we need to show. The first one is that the set S naught is linearly independent. Okay, and then the second thing is you're supposed to show that the span of this S naught here gives the vector space of the 2 by 2 square matrix. Okay, and this F is the field. Okay, so to start with, the first thing I'm going to do is to show that S naught is linearly independent. And already we know S naught to be the vectors 1, 1, 0, 0 as matrix, 1, negative 1, 0, 0, 0, 0, 1, negative 2, and then 0, 0, 1, 2, right? To show that some given set of vectors is linearly independent, we have to just write a span of it, or the linear combination of it, that is it. And then if the only possible way for you to get a linear combination to be 0 is when the coefficients are all 0, then the set is linearly independent. So what we're going to do is we're going to pick this, that, and this one, multiply each of them by some scalars, a1 into the first one, plus a2 into the second one, plus a3 into that, plus a4 into 0, 0, 1, 2. And that should give us the 0 vector here. And then in the 2 by 2 square matrix, the 0 vector is the 0 matrix. Okay. If you simplify all these side and then you sum them, you're going to have a1 plus a2 as the first entry, a1 minus a2 as the second entry, and then a3 plus a4, negative 2a3 plus 2a4. And this should give me 0, 0, 0, 0 as my 0 vector. Okay. Now, what we have here is saying that the matrix on the left is equal to the matrix on the right. So it means their entries should be the same. So a1 plus a2 should give me 0. a1 minus a2 should give me 0. And then from these two equations, I'm using the first two entries, we can add them. Okay, you can call this equation 1, equation 2. When you add these two, you're going to have 2a1 to be equal to 0 because a2 plus negative a2 is 0. And that will mean that a1 is equal to 0. Now, to find a2, we can put a1 to be 0 into the equation 1, this one, and then going to have that 0 plus a2 is 0, so a2 is also 0. Right? And now, if you look at the last two entries here, you can do the same thing. a3 plus a4 should be equal to 0. Sorry. And then negative 2a3 plus 2a4 should be 0. And in this, you can call this equation 3. And then in the last equation, you can actually divide through by 2. And you will have negative a3 plus a4 to be equal to 0. And that is equation 4. So again, if I sum 3 and 4, what is going to happen is that a3 plus negative a3 will give me 0. So I have 0 plus 2a4 equals 0, and that a4 will be equal to 0. If you put a4 in any of these, okay, you're going to have a3 to be equal to 0. So what this whole thing is telling us is that the linear combination of the set in S naught gives the 0 vector only if all the coefficients we pick are equally 0. Okay, and that implies that we have linearly independent set. Okay, so yes, the first part is shown that the set S naught is linearly independent. Now the other part that we are supposed to show is that the span of S0 gives the whole matrix in all the matrices that you can find in the 2x2 square matrix vector space. Okay, so what I mean by the span is that the span of S0 is actually all possible linear combinations you can have. So a1 into the first vector, which is this, plus a2 into the second vector, which is that, a3 into 0 0 1 negative 2, and then you have plus a4 into the last one, 1 2, such that a1, a2, a3, and then a4 are from the field, so they are scalars, right? So what we're going to do here is that you're going to sum this, or try to simplify it as we can. Okay, so the span here, S0 is actually, if you do the simplification, you're going to get the same thing that we had earlier, which is going to give us a1 plus a2, and then a1 minus a2, a3 plus a4, and then negative 2a3 plus 2a4, such that your a1, a2, a3, and a4 are from the fields. So what this whole thing is saying is that this is the span of our given set, and we want to show that every matrix you have in the 2x2 square matrix vector space can be written using the set, or can be written as some scalar times the first one plus some scalar times the second one plus another scalar times that, like that. Okay, so I don't know if it makes sense here. What I want to do is I want to pick any arbitrary matrix in the 2x2 matrix vector space, and then try to write it as some linear combinations of vectors in S0. Okay, all right, so if I pick an arbitrary matrix, say a11, a12, a21, a22, which belong to the 2x2 square matrix vector space, okay, I want to show that this can be written as a scalar multiple of some scalar multiples of the vectors in S0. Remember, you know the vectors in S0 are these vectors. This guy, that, and this. Okay, so you want to make sure that this matrix here can be written as some numbers multiplying them. Okay, and then you summing them together. So the first thing I want to do is to write an equation that, okay, if this belongs to the span, so this matrix that I have here, I want to show that it belongs to the span of S0. If it belongs to the span, then it can be written as this form. Okay, it can be written as the form that we've had here, that is the span of S0 is given by that form. So I want to say that if it belongs to that span, then we can write it as that form, a1 plus a2, a1 minus a2, a3 plus a4. Remember, you know what a1, a2, a3, a4 are. They are the scalars in front of the vectors in S0. Negative 2a3 plus 2a4. Right, so we have that. Now, having that equation, we can say that, so I can write it one more time. Remember that a11, a12, a21, and then a22 are different from the a1, a2, a3 that we are looking at. a1, a2, a3, a4 are just constants in front of, or the scalars in front of the vectors in S0. And then a11, a12, a21, a22 are the entries of any matrix you can pick from the 2x2 square matrix vector space. Okay, that a3 plus a4, negative 2 a3 plus 2a4. Right, this is what we have. So from this, I can say that a1 plus a2 is actually equal to a11, and then, so we have two matrices that are the same, so I'm equating both sides, and then a1 minus A2 is actually equal to A12. I have equation 1, I have equation 2. So if I sum these two equations, 1 plus 2, I'm going to have that 2A1 is equal to A11 plus A12, and then A1 will be equal to A11 plus A12 over 2. Then if I again solve for A2 using this for A1, then A2 in this case will be equal to A11 minus A12 over 2. So we have the scalar that I need in front of some the vectors in S0. So this A1, in terms of these, the entries in the matrix I've picked, that A1 is given by this, and then A2 is also given by that. Okay. Now if you do the same thing for the other entry, you're gonna have A3 plus A4 should be equal to A21, and then negative 2A3 plus 2A4 is equal to A22. If you do solve them simultaneously to get your A3 and then A4, you're going to have that A3 A3 is equal to 2 A21 minus A22 over 4, and then A4 will be equal to 2 A21 plus A22 over 4. So you apply the same method of solving simultaneous equation to solve them. So what this whole thing means is that, what does it mean? It means that if I have any matrix, okay, so any matrix at all in the 2 by 2 square matrix vector space can be written as that. Okay, I've said that already. A21, A22, okay, and that can be equal to some A1 into the first vector in the S0, which is this, plus some A2 into 1, negative 1, 0, 0, plus some A3 into 0, 0, 1, negative 2, I guess, yeah, and A4 into 0, 0, 1, 2. And these scalars that you need to be able to say that indeed this matrix, arbitrary matrix, is true equal to that is when A1 is equal to what we found, okay, and A2 is equal to what we have here, and then in that case we found that A1 was A11 plus A12 divided by 2 in front of that, okay, plus A2 was given as A11 A11 minus A12 over 2 in front of this, negative 1 is 0, 0, plus A3 was given as what? 2A1, A21 actually, minus A22 over 4 into 0, 0, 1, negative 2, plus, okay, let me put this in bracket, plus for the other one, the last one is 2 A21 plus A22 over 4 into 0, 0, 1, 2 as a matrix. So what it means is that these are the elements or the vectors in S0. So every matrix you can pick in M2 by 2 can be written as a linear combination of vectors in S0. And any linear combination you can pick from vectors in S0 is actually belongs to the span. Actually, it belongs to the span. So this belongs to the span of S0. Okay, so the way I use to prove this is that I'm trying to show that every matrix I pick here, okay, actually belongs to every matrix I pick in M2 by 2 belongs to the span of S0. And on the other hand, the span of S0, we know already that was equal to some A1 plus A2 a1 minus a2, a3 plus a4, and then negative 2a3 plus 2a4. And this is a 2 by 2 square matrix. It also, the span of S0 also belongs to the 2 by 2 square matrix. So you have two set. The span is actually a set, and then I have the n2 by 2 square matrix. It's also a set of a whole vectors. I mean, this set of all square matrices that are 2 by 2. And you are saying that the m2 by 2 belong to the span of S0, and then the span of S0 also belongs to the m2 by 2. So this, in set theory, conclude that, so that is a proof that you use to prove that two sets are equal. So this concludes that the m2 by 2 square matrix and the span of S0 are the same, so they are equal. So we've been able to show that one, the set S0 is linearly independent, and that the span of that set is actually the same as the 2 by 2 square matrix over the field F that we are looking at. Okay, so yeah, that is how you show that a given set is actually a basis for a given vector space. Okay, so don't forget to subscribe to my channel if you have not subscribed, and then I will see you in our next lesson. Okay.